Respected leaders and my dear students, hearty welcome to real analysis class. It is a wonderful topic which I love very much because I treat real numbers as God. Yes, it is true. Why? Because you cannot completely describe about the God. You can only say that by seeing certain properties, you can say that he is a generator, organizer and destroyer, something like that. By giving attributes, you can mention about that cosmic energy. On the other hand, your real number system also plays the same role. That is what I feel. It is not possible to define real number system. Why? Because it has n number of attributes. And from childhood we have learned about natural numbers, whole numbers, integers, rational numbers, irrational numbers. So all these are subsets of real numbers. So the real number system contains all these sets. Further it is having three wonderful properties, axioms. Number one, field axiom. 2, ordered axiom, and 3, completeness axiom. First one, field axioms. We are going to define minimum 2 operations on the sets of real numbers, namely plus and dot, and usually we represent it by R. So R with plus should become an abelian group. R minus singletons at 0, that is non-zero real numbers with multiplication forms an abelian group. Apart from that, we should also satisfy the distributive laws, that is A dot B plus C equal to A dot B plus A dot C. Similarly, B plus C dot A, left distributive and right distributive, we know about that. The second one is ordered axiom, comparison. That means when you consider two numbers A and B, law of trichotomy says that either A is greater than B or A is less than B or A is equal to B. Or A can be a positive number or A can be a negative number or A can be equal to 0. And also we are having monotonicity of addition. If A is greater than B and C is any other real number, then automatically A plus C is also greater than B plus C. But when it comes to multiplication, A, C need not be greater than B dot C. If C is positive, we get AC is greater than BC. On the other hand, if C is a negative number, you cannot say that AC becomes less than BC. And then completeness axiom. In order to define completeness axiom, we need little theory behind lower bounds, upper bounds, least upper bounds, greatest lower bounds, least members and greatest member. The completeness property says that if a non-empty set is bounded below, then automatically it has a greatest lower bound. If a non-empty set is bounded above, then we are going to say that it is going to have a supremum. So let us see what are these supremum, infimum and all that. So in order to define supremum and infimum, we can start with a simple example of intervals. Everybody knows about 4 different kinds of intervals. If I take A and B, two numbers on the real axis, we are going to have open interval AB and S2, closed interval A comma B, open at A and closed at B, third one, and closed at A and open at B. And we know that open at AB means that of all real numbers. So for that, all those X lying between A and B. A and B are not included here. Here A and B are included. Here because B is closed, B is included here. Here A is included here. Now what is meant by lower bound? Any number less than this set is called a lower bound. That's all. Very simple. So what are those numbers which are smaller than these numbers? You can easily see that all the numbers lying below A, that means minus infinity to this is the real axis, so it extends from minus infinity to plus infinity. So all those numbers smaller than A, they are called lower bounds. So we say that and A is also a lower bound, though it is not a member of this set. Similarly, this is completely lower bound set, and this is completely upper bound set. So we can say that B to infinity is an upper bound. And the greatest lower bound, we cannot talk about the least lower bound because we cannot reach minus infinity. So we can only talk about the greatest lower bound. A is the greatest lower bound. Here you see. So this is the greatest lower bound and this is least upper bound. And this is called supremum. This is also called supremum and this is called infimum. Okay. So here A is a infimum, B is a supremum, and I told you least number means the member should be present in the given set. Here A is a least number, greatest lower bound, but this is not existing in the set AB, open interval AB. That is why there is no least number. Similarly, there is no greatest number. But when it comes to the second one, clearly you can see in all these cases, these four are common, whereas here in the closed interval, A and B, they are also least numbers and greatest numbers. Similarly, when it comes to closed at B, we get greatest number. Here we get the least number. I hope this is clear to one and all. So any set having these subsets satisfying these properties, that is called real number system. Okay, that is filled axioms, ordered axioms and completeness axiom. What is completeness axiom? A non-empty set which is bounded below has the greatest lower bound. Any non-empty set which is bounded above has a supremum. Bounded above means supremum exists definitely, it assures. That is why it is called completeness axiom. This property is not satisfied by the rational numbers. That is why it has extended to real number system. I hope that is clear. That is the need for the existence of real numbers. I hope this is clear. Thank you very much.